Welcome to today's lesson in physics. Today we are discussing the topic elastic potential energy. As the name suggests, elastic potential energy is the energy stored in the case of springs when they are stretched or compressed. We consider a block of mass m which is connected to one end of a spring, the other end of which is connected to a rigid support. And we consider the mass is negligible, which is connected to the end of the spring. The position of this block when it is at rest and the spring is not stretched or compressed, that is taken as the origin, and it is called as the mean position or equilibrium position, or in short, mean position or equilibrium position of a spring. It is the position it takes when it is at rest. That means neither compressed nor stretched. In that state, what is the position taken by the spring? That's what we mean by the word mean position or equilibrium position. So here in the diagram, this x equal to 0, that x equal to 0 stands for the mean position, and that's what we take as the origin. Now, when the spring is compressed or stretched, first we consider the case when it is stretched. So in order to stretch the spring, we need to apply a force, and due to elasticity within the spring, a force will be developed. That force developed within the spring is called a restoring force because it tries to bring back the spring to its original state. So that restoring force which tries to bring back the spring to the original state, that is also called as spring force. So whenever the spring is deformed from its original state, either by the process of stretching or by compressing, this restoring force comes into action. And according to Newton's third law of motion, this restoring force is equal and opposite to the applied force and is therefore directed along the negative x-axis in this case, because here we have applied the stretching force which is in this direction. So the restoring force which is developed in the spring, it will be in opposite direction. That means like this. Regarding the spring force, we need to keep in mind certain points. That is, the spring force or the restoring force, it is equal in magnitude to the applied force and it is opposite in direction. And one more thing is there, that is, this restoring force is directly proportional to displacement of the block from the mean position. That means to stretch the spring through larger distances or through larger displacements, more force is to be applied. If the applied force is more, restoring force also will be more. That means restoring force is directly proportional to displacement. If the displacement is less, the required force is less and the restoring force also will be less. So that can be stated in the mathematical form like F is proportional to X, where F stands for the restoring force, which is also called as the spring force. More accurately, our equation becomes F is equal to minus Kx. So here K is the constant of proportionality and the negative sign stands for that opposite in direction. That means the displacement and the restoring force developed, they are opposite in direction. If X is positive, F will be negative. If X is negative, F will be positive. Here K, the constant of proportionality, is called as spring constant of the spring or force constant. So spring constant or force constant is represented by K. The equation F is equal to minus Kx is valid only for small displacements. And the negative sign in this expression is because the restoring force is always opposite to the direction of the displacement. And the magnitude of the spring constant is equal to magnitude of restoring force divided by magnitude of displacement. And the value of K can be easily obtained from a load extension graph. Load extension graph means extension is plotted along y-axis and the applied force is taken along x-axis. Such a graph we call as load extension graph, and from that graph this force constant or spring constant can be found out. And the spring constant, as the equation suggests, K is equal to F by X. It is numerically equal to the restoring force per unit displacement, and its SI unit is Newton per meter. And actually this K is also known as stiffness constant of a spring. It is the value of K which decides whether a spring is more or less stiff. The spring constant, it depends on the nature of the material, the way the spring is made, the diameter of the spring, and the diameter of the wire which is used to make the spring. For springs of more stiffness, the value of K will be very large, and for soft springs, the value of K will be small. And we see that the restoring force F is equal to minus Kx. It is not a constant force. It is maximum when the spring is deformed the most, and it is 0 when it is not deformed. Thus, the spring force or the restoring force in a spring is an example of variable force which is conservative. So that is a very important point to be noted. Spring force is a variable force. At the same time, it is a conservative force. So by the property of conservative force, if a work done is there against this conservative force, that work done will be stored as potential energy, and actually that is the origin of elastic potential energy. This diagram shows the three different states of a spring. First one shows equilibrium state, that is there is no displacement, that is x is equal to 0, so the restoring force or the spring force also is 0. In the second case, the spring is stretched, that means x is positive and the restoring force will be acting in the opposite direction, that means Fs is negative. And in the third case, the spring is compressed, that means X is negative, and the restoring force will be acting opposite to that, that means Fs will be positive. Now, this graph shows a plot of spring force versus X. That is, the displacement is taken along x-axis and the spring force is taken along y-axis. So, since the equation is F is equal to minus Kx, we will obtain a graph, a straight line graph, which passes through origin. We have already discussed that area under the force displacement graph gives work done. Here in the graph, the points 0 to B, it shows stretching of the spring from the equilibrium position to an extreme position, that is xm. So when it is stretched from that 0 to xm, that work done by the spring force can be found by finding the area ABO. That means area of the triangle ABO. So by finding the area of the triangle, we get that work done to be half K xm square. So work done by the spring force is minus half K xm square. The same equation we can obtain by the method of integration, because the spring force is a conservative force. So we get the equation to be minus integral 0 to xm fs dx. That means minus integral 0 to xm kx dx. That is equal to minus kxm square by 2. Thus, we generalize the expression for elastic potential energy of a spring which is stretched is half kx square. If it is compressed also, the equation remains same because we have a term x square. So whether it is positive or negative, on squaring, the value remains the same. So this is the important expression for potential energy, which is the elastic potential energy stored in a spring, which is half kx square. Here k stands for spring constant and x stands for the displacement of the spring from its equilibrium position. Now consider a spring which is stretched to a maximum displacement to one side, that is xm, and released. So the maximum displacement of the spring to one side, it is xm. So when it is released to the other side also, it will get compressed through the same displacement xm. So here xm plus or minus xm, it stands for the maximum displacement position on either side of the mean position, and they are called as extreme position. So when such a system, that means a horizontally mounted spring, this arrangement we call as a horizontally mounted spring. That means one end of the spring is connected to a rigid support and the other end is attached to a very small block of mass. And when this free end of the spring is stretched and released, this spring will be making oscillatory motion between the two extreme positions passing through the equilibrium position. So during each oscillation, the spring will be passing through equilibrium position also. So that maximum displacement positions on either side of equilibrium position is called as extreme positions. We already stated that the spring force is a conservative force. So in the case of conservative force, the total mechanical energy of a system remains constant. So in this case, when this block of mass, it makes oscillation about the equilibrium position, that block of mass, it is having two types of energy, kinetic energy and the potential energy. That potential energy is possessed by the elastic nature of that spring, and that is given by half kx square. And kinetic energy is given by the expression half mv square, where m is the mass of that block which is connected to the spring and v is its velocity. Now coming to that potential energy term half kx square, we know that the potential energy will be maximum at the extreme position, and that maximum potential energy, it will be half kxm square. And we know at the extreme positions, kinetic energy will be equal to 0, because at the extreme position, the wooden or the mass which is connected to that spring, it is coming to rest for a moment. That means its velocity is becoming 0 at the extreme positions. So the kinetic energy of the system at the extreme positions will be equal to 0. So we can conclude that the total mechanical energy of the system is purely potential at the extreme positions, and at the mean position or at the equilibrium position, that total mechanical energy is purely kinetic, because at x equal to 0, potential energy is becoming 0. So that energy, the total mechanical energy of the system at the equilibrium position will be purely kinetic. So actually during this oscillation of this system, between the two extreme positions, there is transformation of energy from one form to another form. So at extreme position, energy is purely potential, and at the mean position or the equilibrium position, the total energy is purely kinetic. So in between, we can say that means at any position between an extreme position and equilibrium position, that total energy will be the sum of kinetic energy and potential energy. But since the system is a conservative force system, or the force acting is a conservative force, the total mechanical energy remains constant. So the sum of mechanical energy at any instant of motion of this particular system, that total mechanical energy will be remaining constant. Total mechanical energy means the sum of kinetic energy and potential energy. So for this particular system, we can frame an equation which is given by half k xm square equal to half kx square plus half m v square. Here right hand side shows the sum of kinetic energy and potential energy at any position of the motion, and the left hand side shows the total mechanical energy, and that total mechanical energy we write as half k xm square, because we know the total mechanical energy is purely potential at the extreme position, and we know that at the extreme positions the potential energy is given by half k xm square. Because of that, we have this equation: half k xm square is equal to half kx square plus half m v square. And we know at the equilibrium position x is equal to 0, and we have half m vm square is equal to half k xm square. That means the system is having maximum kinetic energy at the mean position, and at the mean position the system has maximum velocity or maximum speed also, and that maximum speed or maximum velocity is given by the expression Vm is equal to root of k by m into xm. This equation we are obtaining by rearranging the previous expression. This is the graph showing the variation of kinetic energy, potential energy, and the total energy of a system. That means a block which is attached to a horizontally mounted spring. For that system, how does the kinetic energy, potential energy, and total energy vary? That is given by this graph. So as we stated, at the extreme positions, the energy is purely potential, and at the main position the total energy is purely kinetic. So that blue curve, it stands for the kinetic energy, and the ash color curve stands for potential energy, and that straight line, that stands for the total energy, and as we know the total mechanical energy remains constant. Here in the slide, one word Hooke's law is mentioned. Hooke's law is nothing but that equation F is equal to minus kx. The nature of spring force we are stating with that expression F is equal to minus kx, and that equation is termed as Hooke's law. Now we will discuss one problem, that is example 6.8. To simulate car accidents, auto manufacturers study the collisions of moving cars with mounted springs of different spring constants. Consider a typical simulation with a car of mass 1000 kg moving with a speed 18 km per hour on a smooth road and colliding with a horizontally mounted spring of spring constant 6.25 into 10 raised to 3 Newton per meter. What is the maximum compression of the spring? So here something is mentioned about that simulation of car accidents. That is for the purpose of studies in the laboratory. So here what is happening is the car is making collision with the spring. So when the car is in motion, it is having kinetic energy, and when it collides with the spring is getting compressed. So when the spring gets compressed to the maximum, the car is coming to rest. So here also, since the forces involved are the conservative forces, the total mechanical energy should be conserved. That means what was the incoming kinetic energy of the car, that should be equal to the potential energy stored in the spring. That means we can equate half mv square to half kx square, and we are asked to find maximum compression. So for maximum compression, the expression for potential energy stored, it becomes half kxm square. So half kxm square is equal to the kinetic energy. Kinetic energy can easily found using the equation half mv square, where m is the mass and v is the speed. So here m is given as 1000 kilogram and the speed is 18 kilometer per hour, which is the same as 5 meter per second. How can we convert kilometer per hour to meter per second? That is by multiplying with 5 by 18. So 18 into 5 by 18 will get 5, that is 5 meter per second. So on substitution, we will get the kinetic energy to be 1.25 into 10 raised to 4 joule. Now, finding the displacement, we have that kinetic energy of the car is equal to the potential energy of the spring when it is maximum compressed. That is half kxm square is equal to that potential energy, and we get the value of xm from that equation to be 2 meter. With that, we conclude today's lesson. Thank you.